Okay, let's do one more result. This time it'll be really an actual theorem, something a little more general than what we just did with the empty set. So let's write down here that we have a theorem. Let's say let A be any set. Now that could be a set among the real numbers or in Rn or any, it could be any kind of set. Finite set, could be any kind of set. So we're going to say if SA is an open set, for every A in A, that doesn't look so good. Let's fix that here. Let's put this down here. For every A in A, then the union over all of the elements of capital A, of the sets SA, is an open set. So you recall that we actually proved this theorem in the case of capital A being a two-element set. If we took the union of just two sets, say S1 and S2, we might even have used S1 and S2 as the sets then, I don't recall. We proved the theorem that the union of two open sets is itself an open set. So this is saying that A could have n elements. So this could be the union of n sets. But A could be any set, might not be finite. So this could be A1, A2, A3, A4, sorry, S1, S2, S3, S4, and so on. And if they're all open, the union's an open set. I'm going to write this in a different way as well. So there's another way we could write this that can help to clarify maybe. And so this is equal to the union of the set of sets SA such that A is in A. So these are just two different ways of writing the same thing. We're taking the union of all the sets S sub A over all the A, little a's in capital A, and I'm going to write this as, so I don't have to keep writing this a little more stuff to write here. I'm just going to write this as S for our purposes right here. And so we're going to give a proof of that. And hopefully this proof, as we do it, will provide a little more insight into the strategy of how we often do prove things. And in that strategy, or in the proving, we're going to be using some of the features of implication that we talked about a little earlier. But first, let's do a few examples, really two examples, but a couple of them. One of them is kind of an extended example of what's going on here. So we can get kind of a better feel for what this union of possibly an infinite number of sets might be. So over here, let's say we'll do some examples. And let's say our first example, we'll say for every A in R plus plus, for every strictly positive number A, every strictly positive real number. So here, of course, R plus plus, for the moment, would be playing the role of capital A, although we haven't actually got the theorem. We're not actually applying the theorem yet. Let S sub A be the open interval in R from A minus 1 over A to A plus 1 over A. And so you'll notice, first of all, this is well defined because A can never be 0. I'm only looking at A's that are strictly positive. So this number here and this number here, they're both well defined. Also notice that the length or the width of this interval grows very small when A is big, right? And if A is like 1,000,000, then this is 1,000,000 minus 1/1,000,000th. This is 1,000,000 plus 1/1,000,000th. The width would be just 2/1,000,000ths. So let's just say, note the length of the interval SA, and I'll use that little L just to mean the length, that's going to be just 2 over A. And if A is really big, then the interval is really small in R. And note too that SA is open for every A. So this is always an open set in R. It's an open interval in R. So then for any set A, the union over all A in A of S sub A is an open set in R, because, of course, this is an open set in R, and so if I have a whole bunch of such sets and take the union, that's going to be a set in R as well. So this is an open set, and so take some specific examples. You could say, let A be a 2-element set, any 2-element set. In particular, let it be just 1 and 2. So then, and let's call this S here as well. I used S over here, so let's call this S, to give it a shorthand name. Then, in this case, S happens to be the interval from 0 to 2.5, the open interval. It's easy to see. Okay, S1 is the open interval from 0 to 2, and S2 is the interval from 1.5 to 2.5. And I take the union, I get everything from 0 to 2.5, not including the endpoints. You could see what happens if A has n elements. You can think for yourself about what happens, and you could prove, oh, and by the way, let's just note that we've already proved this. We've proved that's open. Of course, it's an open interval here, but if I'd taken any 2 numbers here, we'd say we already proved that this is always an open set for any 2-element set A. This proof is the same. Instead of doing 2 cases, which is the way we proved this when there were only 2 sets, we looked at the case when an X was in the first set, and then the case when X was in the second set, so that we looked at every X that could be in the union in S. Here we would just look at n cases if we had n sets. If we had A has n elements, so there are n sets S1 to Sn, let's say. What about the case when A is all the natural numbers, which is, again, that is a subset of R++. I'll leave that for you to think about. You can kind of see sort of what's going on. I'm getting a bunch of smaller and smaller and smaller open intervals, always centered on an integer as I go infinitely far out. That's going to be an open set. Let's consider the case where A is, let's say, the rationals intersected with the interval from 1 to infinity, let's say. You can think about what this set is, and I'll write down here that this set is R++. Finally, consider the case where A is itself all of R++. In that case, this is wrong here. This is wrong. If A is this, then S is R++. And if A is itself R++, S is all of R. Okay, so both of those, this instance of the example And this instance of the example, I leave to you to verify for yourself that indeed, if A is this set, then S, this union, will be all of R plus plus and nothing more. And if A is all of R plus plus, then S, this union, is actually all of R. You can see that pretty easily. Second example, let's let X it could be any kind of a set, but let's say it's a subset of Rn, because we're used to thinking about sets in Rn. And let's define script capital E to be the set of all subsets of capital X such that E is open. It's the set of all open subsets of our set capital X, whatever capital X is. X could be the unit circle, X could be the positive quadrant, X could be any subset of Rn. This is the E, script E is the collection of all the open subsets of capital X. And let's define something called INT of X to be the union over all E's in script E of E. All right, so in other words, this is the collection of all open subsets of X. This INT of X is the union of all those sets. That is, it's the union of all the open subsets of capital X. INT stands for interior. And so this is something that we probably won't use again in this course, but you will probably use it in the next course that you do in any kind of mathematics to support economics. So this is called the interior of the set X. We may come back and see it in this course here at some point. This is called the interior of the set X, and it is, by definition, the union of all the open subsets of capital X. And, of course, that's open then I'm not very good at writing this kind of right below my below, so maybe the way to do that is for me to get lower here, and then I'll write the interior of X is an open set. And of course, that comes from this theorem, which we have yet to prove. So it's an open set because here we're going to prove that anytime we have a bunch of open sets and take the union, that's going to be an open set. And so let me point out that this does fit the theorem exactly, because this is playing the role of capital A in the theorem. This is playing the role of the little a's in the theorem. And this is playing the role of the S sub a's in the theorem. And you might say, but wait a minute, how can E be playing the role of little a and S sub a at the same time? And that's just because for every A, that is for every set, we're using that set both as the index here and as the set itself. So that's not really a problem. And so this fits exactly with the statement of the theorem, where we can see what's playing the role of each item in the theorem, or another way to say it, what each of the items in this union is playing the role of over here. And so the interior is an open set. So it's just some examples of how this theorem might be applied. In fact, is applied in these cases. Okay, so now let's see if we can do a proof of this theorem. So I think it's a good kind of practice when you're first doing these proofs to write down what it is that we're assuming and write down where it is we have to go, what it is we have to prove, so that we can identify the space between them, the stuff we have to kind of fill in and prove. And sometimes we can work backwards from what it is we have to get to and work forwards from the things we've assumed to see what we can drive until we can kind of get things all pulled together so that we've kind of filled in all the blanks between them. So here we're going to say what we want to assume is that for all elements of the set capital A, S sub A is an open set. So let's just write SA is open. So we've got some set, any set. It kind of indexes all these open sets, and so each one of these sets is open. And we want to prove that this set S, that I've used as a shorthand here, is open. And so I could say I want to prove that S is open, but in fact, let's write down the definition of what it means to be open. So we want to prove that for every X in S, there exists an epsilon greater than 0 such that the ball around X of radius epsilon is a subset of S, because that's the definition of S being an open set. Okay, so here we have a universal quantifier for every X in S. We need to prove this is true. So whenever we have to prove something involving a universal quantifier like this, the typical thing that we do, I would say almost always that what we want to do, is we want to then say, let's take a typical X, a typical one of these things. This says we have to prove that something is true for every one. Let's take a typical one or an arbitrary one. And so what we would do here is we would say, okay, let X be in S, or, and I'm going to write it assume again, assume, I'll say, that X is in S. And now what we want to prove, I've got a typical X. I need to prove this is true for that typical X. So I need to prove that there exists an epsilon greater than 0 such that B of X and epsilon is a subset of S. So notice what, in a sense, what it is we've done here. We've taken this universal statement, which we need to prove, and we have turned it into an open statement with a free variable X by saying, let's pick a typical X. Let's take an arbitrary X in S, assuming that we have some X in S. We're going to prove that this is so for that X. So now we're going to, from here on, anything we do is going to be with open statements. So we're going to have open statements now. So this is an open statement. And as we go down here, the succeeding statements that come from this are presumably also going to be open statements about the typical X. Okay, so we want to prove this. And so when we want to prove something about an existential statement, what we need to do, unlike this, where we wanted to prove something about a universal statement, so we picked a typical X, or an arbitrary X that is in S, this existential statement, we have to come up with an epsilon that will work for this, that will do this. And so that can be the tricky part here. So here, what we'll do is we'll say, well, we have to do this for a typical X, and well, that typical X that's in S, what do we know? What do we know about a typical X that's in S? Well, if X is in S, that means X is in this union. And that means it's actually in one of the S sub A's. So what we have is from, and now what I'm going to do here, I'm going to go back, let's use a different color for this. Let's use this color here. This, I'm going to say, and in fact, let's even do this. Let's say that's the statement P. That's a closed statement. And I want to prove, well, I want to prove this thing here. So let's go and do that this way here. I want to prove P implies Q. So prove P implies Q. So now let's take this open statement. I'll call it P prime. I could call it P prime of X because it's an open statement, and so, to be complete, it would be nice to write this, but I'm actually not. I'll write it here, but I'm just going to use P prime for this for the most part. And I want to prove this down here, which I'll call Q prime, which is also an open statement with the variable X in it. Notice that the variable epsilon is not open. It's not free because it's been quantified here. So I want to prove that P prime of X implies Q prime of X for any X, for a typical X. So what we have now, we could say, is from P prime, we have X in S, but that means that X is in this set here. It's in this union, and that means it has to be actually in one of the sets SA. So that says there exists an A in capital A such that X is in SA. And then it's also true, so what I'm doing here is I'm just trying to go back to the things we've assumed and see what we can pull out as implications from the things that we've assumed. So we now know that this typical X is in some one of the sets SA, could be in more than one, and we know from P here that we've assumed that SA is open. So let's say that SA is open. And so, therefore, from those two, we have, and from the definition of an open set, we know that there exists an epsilon greater than 0 such that the ball around X of radius epsilon is a subset of S sub A. And that is a subset of the union of all A's in capital A, SA, which is S, which would complete the proof except for one thing, and that is here I've used little lowercase a as the index set here, and here I've got A as a particular A, so that isn't quite kosher there. So what I really want to do is be a little more careful here where I said there exists some A that's in A. This is correct, but then when I get down to using this here, I've got a little bit of confusion between this particular A and this A, which is a kind of a dummy variable or an index here. So what I want to do is say there exists an A in A such that X is in SA, and so let's say that I could do that in a number of ways. And so what I'm going to do is I'm going to say that for this typical X that I chose, this arbitrary X, there exists an A for that X. So I'll call this A sub X. And so that means this is A sub X. And then I have that there exists an epsilon, and that epsilon depends on the X. So I would have an X here also. And this would be sub X. But here it's not any sub X because this is the index on our set here. So, now I actually have that there exists an epsilon greater than 0 such that the ball around our typical X of radius epsilon is a subset of S sub A, and that S sub A is a subset, of course, of our capital S, of this union. So we are done. I should perhaps point out that this does depend on the fact that, well, actually, that's not true. We're actually not done. We're not done because we'll see why here. And that's because everything here was done for the typical x. So I did this little squiggly pink arrow here. Well, actually, that was to indicate that everything down here would be now an open statement. I should now continue this little squiggly arrow all the way down to here, because everything now down here is they're all open statements about the typical x that we did here. But of course, it's a typical or arbitrary x in S. So that means that this open statement, the open statements that we've got here, they're going to be true for every x in S. So since x was an arbitrary x in S, so it was arbitrary except that it was in S, we have for every x in S, what we have just done here is true. So for every x in S, there exists an epsilon, and now we could write it, in fact. I'll continue to, well, I'll write the little pink x back in a moment. There exists an epsilon such that the ball around x of radius epsilon is a subset of S. And that completes the proof. And I could go back and put the little x down here and the little x over here. And so we do have to go back and take our open statements that we obtained from here and quantify them. And in this case, of course, because we have an arbitrary x in here, we've got this true for every x in S. And finally, let me do one more thing here, and that is let me rewrite the proof as we would typically do, because here I've gone through this intentionally in a way that it tries to give you an idea of the strategy of how to go about constructing a proof when it's not clear how to do it, what kind of steps we need to take. Now, it's not an algorithm. We can't write down an algorithm for how to prove things, but this gives some strategy for how to go about doing this. But let me give a proof with less detail. So let's say, leaving out some of the, maybe a fewer details, okay, how I would go about this. So I'm going to do the same proof. And out here, now I would just say, let A be an A. In fact, I would probably just say that what I need to do here is I would simply say let X be in S. So then there exists an A in A such that X is in SA. SA is open, therefore there exists an epsilon greater than 0 such that the ball around X of radius epsilon is a subset of SA, and that is a subset of the union of all A's, A, SA, and that completes the proof except for the same issue I had down here. Here I have to be a little careful about this. I would say there exists an A sub X, or I might have just said there exists some A bar. That would be an alternative to writing that little sub X down there. I would say there exists some particular A in the set capital A such that x is in that set. S, this should have a bar on it. That SA bar is open, and so there exists an epsilon greater than 0, such that the ball around x of radius epsilon is a subset of SA bar, which is a subset of this. So you can see that leaving out a lot of the detail, we get a nice, clean, short, concise proof. But of course, being able to write it like this takes some practice, takes some experience. And the issue isn't to write it like this. The issue is to see what the proof actually is, to see how to do the proof. And once we get some experience how to do them, it becomes a little easier to write them in a concise form like this, rather than all the detail I've done over here. So we've actually done quite a bit in our lecture, or actually our two-part lecture today. It's pretty long. And I think this gives us a pretty good idea of some of the issues in using symbolic logic and using the symbolic logic to actually construct proofs. And so that's it for today. See you all next time.